Hello everyone. Let's get started. In our last video, I think video number 10, right? In that video, we derived the indicial notation for determinant of a matrix. Okay. In this video, I'm going to extend our discussion further into the matrix or tensor side. Okay. Right. So here in this video, first we discuss the multiplication of two matrix or two tensor, right? Okay. Let's say matrix A cross, that means A and B. In our continuum mechanics, we mostly deal with 3 by 3 matrix, but the index notation, it's applicable for any dimensions. But the rules and everything we use for 3-dimension case, right? So in our case, this is 3 by 3 matrix. So this is also 3 by 3 matrix. You know the matrix multiplication rule, right? The first matrix, the column, the second matrix row must be same, right? So that means these three will catenate each other. Then finally, you will end up with one C matrix. So that is again 3 by 3. Okay. This is the matrix multiplication rule. Similarly, a vector, let's say a vector V. Vector V in matrix notation, I told you, we represent by 3 by 1 vector. So that means 3 rows and 1 column. Okay. When you multiply vector into a matrix, so let's say vector V, and you are multiplying by matrix A, 3 by 3. You cannot multiply vector and matrix in this way. That means you write a vector pre-multiply to A. So you cannot multiply this way because it is not satisfying the rules, right? These two must be same. You cannot catenate these two. So therefore you cannot multiply this way, right? But if you write it other way, if you write the matrix as free multiplied to the vector, so that means this is now 3 by 3 matrix. So vector V now 3 by 1 matrix. So now these three, now you can apply the multiplication rule. Then finally you will get a vector because 3 by 1. This is the vector now. Okay. These some multiplication things rule you studied in your mathematics, in your matrix algebra, right? Just I am refreshing those things. This one, the first one, right? You can make as a multiplication. That means valid multiplication. How? Instead of vector V, you can write transform of that vector into matrix A now. Transform of vector means the column, you write it as a row now. Now this will become now 1 by 3. This is now 3 by 3. So now you will get, what is that? 1 by 3 matrix. That means now the vector, it is transpose, right? Now you will get transpose of the previous vector. Okay, right. Let's discuss these things to index notation, right? The first I will take this one, right? Vector U is equal matrix A into vector V. How can you write it as an index notation, right? First, I will write the left-hand side. If it is vector, you need one free index, right? Ui. So therefore, you should have free index right side of the equation, the same free index I, right? You must remember. Because right side of the equation now, this one also a vector. Because A into V is the vector, right? 3 by 1. Okay. So now I'm going to write, you have to be very careful. I have to write it in a one index, the free index, right? Okay. Now A into. So now when I want to multiply this rule, the previous matrix number of column in the matrix equal to number of rows in the vector, right? Number of rows in the vector actually, that is the subscript numbers, right? V1, V2, V3. So therefore, the repeated index must be, for example, if I take this is J, the same J should be here in this matrix for the number of columns, right? So to represent this one, right? So now free index I will be here. Now this is satisfying the multiplication rule, right? JJ 3 3. So this is the index notation for matrix multiplication, right? So that means this side I is a free index, the right hand side I is a free index, right? Okay. Right. Right. So this is very important stuff, right? Okay. This is one thing. Okay. Right. But we already discussed this one, right? Aij matrix A you can represent by Aij, right? This is we already discussed, right? Okay. I will discuss one more thing here. This is already we discussed. If you want to write transpose of one matrix, what is the meaning of transpose? You write column as a row in the second matrix, right? You transpose. So that means the first column now the first one is number of rows, right? The rows now become a column now become a rows, right? So that means this I and J, I represent the row index, J represent the column index. This I and J must be interchanged, right? So that means AJI. Okay, so this is my A transpose, right? So this also you must understand this one, right? The index notation of the matrix. Okay, right. So now I'm going to write the index notation of matrix multiplication, right? Matrix A, matrix B equal matrix C. First, I will write matrix C here. I will introduce I and J. Okay, equal. Now again, I and J, left side of the equation, it's a free index. So therefore, right side of the equation must have the same free index. Okay. Then AB, the first matrix number of column, the second matrix number of row must be same, right? So therefore, A, first I will write that repeated index condition. First matrix number of row, the number of column, then second matrix number of rows must be same. KK. Now I want to write the first subscript of A and second subscript of B. Those two should be the same free index because you have to introduce the free index here, right? So that means I here, J here. This is the index notation for the matrix multiplication, right? Okay. Right. Here, I am giving one more exercise, right? Example, just think this way, right? Let's say if someone give this way, Ij A K I B K J. If you get this type of index notation, can you say it is wrong? No, you cannot say wrong. Why I am saying it, why I am asking, can you say wrong? Because you see, the number of uh, column and number of row must be same, right? But when I write other side, can you say it is wrong? We cannot, because here our case is 3 by 3 matrix. Okay. Then you can see this equation. The left side of the equation 2 free index, ij free index. Right side also ij free index, because k is a repeated index. Okay. If you want to make the multiplication rule, you have to interchange I and k, right? So that means if you change I and k means, what is that? It is actually transpose, right? So what is actually this one? This is actually A transpose into B. Because A, if AIK, then A transpose AKI, right? So in this case, because our matrix is 3 by 3 matrix, we can write this way also, right? Okay. These are very important, right? We need these stuffs when we discuss the another part, the new part we are going to start in this video, right? Okay. Right. I think, yeah, this all right. Then other than that, we discussed the identity matrix, right? If you write identity matrix, the matrix notation, let's say Ij, right? This is also we discussed, this is our Kronecker delta. Okay. Kronecker delta is our identity matrix, right? Okay. This also we discussed already, but just I am generalizing in terms of the matrix notation, right? Okay. Okay. So in this video, we are moving now some advanced topics, right? In linear algebra. But what you studied in your linear algebra, now I am going to use that linear algebra stuff for continuum mechanics part, right? Okay. This part, now I am going to discuss here. That means change of base. What do you mean by change of base? Changing the base vector. That means changing your frame of reference. That means changing your uh, coordinate system, right? You have one coordinate system. I'm going to change that coordinate system to another coordinate system. So you have one coordinate system based on the right hand rule. You have x-axis, y-axis, and z-axis, right? In these three axes, you can move this one into the different location. How can you move? One is just translation. Just move the coordinate system without changing the orientation, just moving one side. Then also you can rotate the coordinate system, right? Okay, right. So moving the coordinate system, it is not a difficult, just one vector, right? So each vector, just we will add to the previous coordinate. That's all. Okay. Now we are going to discuss here the rotation. When you rotate the basis, how this going to change? Why translation is not matter? For example, let's say the previous one, right? Let's say two dimension case, x and y. Now this is the previous origin. Now this origin, you move it to the different location, right? Without rotating the coordinate system. Now let's say x bar, y bar. If you measure any point from this coordinate, if you want to convert to the previous coordinate, not a problem, right? So this movement, you have a vector u. If you know this vector u, wherever the x coordinate you measure from here, you just add the previous x coordinate to here. Similarly, the y coordinate. That's all, right? It's not a difficult case. Okay. If you know the translation vector, you can simply convert. Now we are going to discuss the rotation things, right? Actually, three-dimension rotation, but it's very difficult to explain when I draw the three-dimension rotation. Let me draw it the two dimension. Two dimension here. Actually, I'm considering the three dimension case, but I don't change the z axis. So that means x axis here. Now y axis here. Okay. So this is now our previous axis, right? Let's say x1. This is my x2. x3 perpendicular to this one, right? It's perpendicular to this one because if I apply the right hand rule. Now what I'm going to do, keeping x3 same, I'm rotating x1, x2 plan only. x3 is same. With respect to x3 axis, I am rotating this axis, right? What I mean here, this is my x and y axis, z axis here, okay? I keep, with respect to z axis, I rotate x and y, right? That means z axis is still the same, right? Okay. So now z axis is here along towards me, right? So that means this is my x3. Okay, right. Now what I'm going to do, I'm going to rotate these coordinate systems on one angle, right? Okay, this is my x1 axis now, the new x1. Then this is my new x2. Okay, yeah, yeah. So this is my x1 now bar. This is my x2 bar. Okay, right. Yes. So now the previous x1, x2, for here, for this case, I have now the base vector, right? E1, E2, E3. Similarly, I will have the base vector for bar coordinate system, right? So let me take some definition, right? Base vector for unbar, right? Unbar coordinate system E1, E2, E3, right? So that means in index notation, I can say EI. Okay, so these are the vector. Yeah. For base vector for bar coordinate system, right? Bar system. This is now E1 bar, E2 bar, E3 bar, right? These are the vector, right? So now if I represent in index notation, this is EI bar, right? Okay. So this below line for the to represent the vector, right? Okay. Right. So now what I'm going to consider, I'm going to take one vector here, right? Let's say this is my vector V. Okay. Let me increase the width. Yeah. Yes. Okay. Yeah. So this one now, it is my vector V. V vector. This vector V is same V vector for both cases. Vector is same. Only thing, this vector I'm going to decompose in two different coordinate system. Vector is still same, right? So for example, if I want to take from the unbar coordinate system, so this is my the x component, right? Similarly, this is my y component. So that means this is my x1 component, this is my x2 component, right? So that means this is my v1 component, this is my v2 component, right? Similarly, if I want to decompose the same vector into bar coordinate system, I have to write perpendicular to that one, right? Okay, perpendicular line. Now this is my V1 bar. Similarly, if I write perpendicular to X2 bar axis, this is my V2 bar. V3 in both cases same, right? Because I don't change the X3 axis, right? Okay. Right. So now if I want to represent vector V in terms of unbar coordinate system, this will be like V1. Okay, I'll write it again. First V1 E1 plus V2 E2 plus V3 E3. This is actually VI EI. If I write it index notation, right? Okay. Similarly, the same V vector, I can write it in bar coordinate system. That means V1 bar, E1 bar, right? Similarly, V2 bar, E2 bar, right? Okay. So in this case, I consider E3 and E3 bar is same, right? But in general, in my diagram, I consider same because it's difficult to draw the diagram. That's why I consider the simplification case. But in general, you can rotate any orientation, right? So in this case, I will write V3 bar, E3 bar. It's a different, right? Okay. Now I can write this one in index notation form, right? VI EI bar, right? Okay. But in both cases, same vector, right? Same vector, I represent both two different coordinate system, but vector is same, resultant is same vector, same force. I decompose into two different systems. That's all, right? So therefore, these two is same, right? Okay. Now I can write this one, right? VI EI, right? Equal VI bar EI bar. Okay. Because these both are same vector, vector V, right? I will write vector V also, right? Okay. Without confusing now, right? So now I'm going to consider these two part only, right? For further discussion. All right. Before discussing these things, the definition of dot product of EI, EJ, right? EI, EJ. Okay. This is we discuss delta IJ. You must be very careful. This is most of the student confusing in this point. What is that point? The base vector belongs to one reference system. For example, EI, EJ based on unbar coordinate system. For example, EI base vector in unbar coordinate system dot product with base vector of bar coordinate system. This is not delta IJ. This is not delta IJ. This is wrong. Because these two different coordinate system base vector. This is our normal dot product. Okay. Again, when you multiply two vector, right? It's actually the matrix multiplication, right? So when you multiply two vector u into v, you cannot simply multiply because 3 by 1 into 3 by 1, you cannot multiply, right? You have to change, right? Let's say vector u, vector v. You cannot multiply like this, right? So only thing, one matrix you have to transpose, right? U vector, v transpose, right? So that means now this is 3 by 1. This is 1 by 3. Now this will be 3 by 3 matrix. Okay, you will get now one matrix now. Okay. Right. Clear? Right. If you want to write it index notation, ui, this is, you will write it as vj because transpose is same, right? Because it is vector is same, but only thing you can put right transpose, right? So this is ij, right? Okay. You can write it like this, right? Okay. So be careful this one, right? So therefore, this is not delta ij. This is some vector, right? Okay. Right. But again, if it is ei bar dot product with ej bar, now the same coordinate system, both are base vector, dot product of base vector, now delta ij. This is correct. But this is wrong, right? Be careful, right? Okay. Right. So now what I'm going to do, vi ei bar vj, sorry, vi, right? Vi bar ei bar, right? Okay. Now what I'm going to do, I'm going to multiply both sides by unbar base vector dot product, right? When you multiply dot product with unbar, I cannot write again ei, right? This should be ei, right? Not ej. This is ei. Okay, vi, yeah, right? Okay, vi, ei, right? Yeah. I cannot write again I because we have a rule, right? The if because I is a free index here, you cannot repeat I more than 2, right? So now you cannot, but you have to write the different subscript, right? Let's say ej. I will multiply ej both side of the equation, right? So now the left side, right? Vi ei dot ej. Both are base vector with same coordinate system. Both are unbar. Therefore, this one I can write delta ij. Okay, equal vi bar. This one, it is not a delta ij because both base vector belongs to different coordinate system. Therefore, you have to get the matrix. This matrix, how we are writing here, I will write as R I J. Okay, when I write this one, when I write Rij, very be careful the notation, right? The first subscript, it is belong to bar coordinate system, right? The J belongs to unbar coordinate system, right? So therefore, in this case, the one I have written here, right? If you want to write this case, right? If you want to write this case, if you want to write this notation here, you will put R. First, you have to write the bar coordinate system subscript. What is the bar coordinate subscript? J. Then unbar. Okay. Very be careful, right? Okay. So this is the way I define, right? But someone can define other way also, no issue. But this is the way I define because this is the way most of the books they define, right? Let's be consistent with the research community. So therefore, I will follow the same convention what they use, right? Okay. Now this is right. Now let me copy this one. I'm going to turn the page. Okay. Right. So now we discussed already, right? the properties of delta. When you multiply delta, the same subscript you have to remove the combined remaining one, right? So therefore, the left side now Vj, right side same, right? Vi, it is Vi, right? Vi bar, because these two now it's a number, right? I can write it this way also, right? I will write R front, right? Okay, easiness, right? Rij Vi, right? Okay, right. Okay, because this is just a number, right? Because this is just a number, right? I can switch. Okay, right. Now, what is the check whether this equation is correct or not. The left side, j is a free index now. It is a vector. Right side, I is repeated index. J is a free index. Therefore, vector. Free index is satisfy both sides of the equation. That's all. Now, let's change it to the matrix notation now, right? So this is vector v equal. Now, this is the what we discussed already, right? When you multiply vector and scalar, right? Let me go to the one previously we discussed, right? You see, when you multiply matrix and vector, the last subscript of matrix and last subscript of vector must be same, right? That is the proper multiplication, right? In this case, it is not like that, right? So that means I have to switch I and j, right? So that means if I switch I and j, if I write ji, that is actually transpose of the previous one, right? We discussed if we switch this one, it is a transpose, right? This is therefore when instead of ij, I can write ji transform, right? If I do the transform to this matrix, I will get the previous one, right? Okay, vi. Now the multiplication is satisfied, right? Right? Okay. So I will write one more step, right? For your understanding. Now I can write now simply the matrix notation. Now matrix R into Vi, sorry, not Vi, V bar, right? Okay, right. So this is something you studied. Maybe in your finite element, someone studied matrix analysis of structure. You might have studied this one, right? The rotation matrix. In previous case, we discussed this one, right? Vi Ei equal Vi bar Ei bar, right? Previously, I multiply by unbar base, right? Same thing now, what I can do, I can multiply by bar, right? Bar coordinate, that means bar base vector in both sides, right? Okay. Okay, I'll write one more steps, right? Pi Ei. Now I will multiply by dot product with Ej. Now bar coordinate system, right? Equal Vi bar Ei bar. Now dot product with Ej, right? Bar coordinate system. Right. So now you can see this is Vi. Again, bar, unbar coordinate system. Now it's a matrix, right? R. You have to write first bar one, right? J, unbar, right? Don't forget this one, my convention, right? Bar, unbar, right? Okay. Equal Vi bar Ei. Now the base vector in same reference frame, right? Both are same base vector with respect to same coordinate axis. Therefore, now delta ij, right? Delta ij. Okay. So now if I write it, okay, now the right side, okay, I'll write it one more steps. I'll switch, right? The right side, left side, right? So first I will write Vi delta Ij, right? Then properties of delta, I cancel out. V bar J equal this one, Rji Vi, right? Now this is directly following this multiplication rule, right? I. No issue, right? So now this one, if I write it in the matrix form, bar coordinate system vector rotation matrix into unbarred. Okay. So this is the two things you studied in your finite element, right? The same thing I have proved using the index notation, right? Okay. So let me stop this video at this point. Then we will continue. There are many interesting stuffs. So we can discuss, right? In the continuation of this part in next video, right? So again, please subscribe. Please subscribe and share with others, right? Like and subscribe, share with others, because we need some subscription, right? Therefore, your help. This is I am doing like just to help others, right? Even help to our institute. Just if you subscribe this one, it will help us to reach our video with a lot of that mean most of the even other countries students as well, right? Okay, then see you in next video.